So welcome to this lecture on field programmable gate arrays and the course design with digital system design with PLDs and FPGAs. In the last lecture we have looked at the architecture of complex PLD. Essentially we have looked at the logic block, the interconnect switch architecture. In the logic block we have looked at the product term array, product term allocator. The macro cell consists of flip-flops with certain configurable options, and we have looked at a given a VHDL code, how it is synthesized, then kind of place and fitted that synthesized circuit within the CPLD. Okay, and we also have seen the timing model of it and the IO block and various applications and some kind of features of CPLDs. And today we are going to look at much more popular class of devices called field programmable gate arrays. And before that we just look at the previous lecture slide so that we can contrast the FPGAs or field programmable gate arrays with the CPLDs, complex programmable logic devices. I mean, why the FPGAs are much more popular, much more used than CPLD, we will be able to understand if you briefly look at it, the CPLD part, and go to the FPGA. So let us turn to the slides of the last lecture. So we had looked at the MAX 7000 PLD, which is from Altera, as an example, and we said the CPLDs are kind of hierarchical PLD which consists of simple PLD blocks which is interconnected through a switch. So these are 16 macro cell, that means kind of handover with the programmable flip-flops. Such 16 outputs, and here it is shown 4 blocks, and there is an interconnection, and the AND gates input goes from the output of this huge switch. Like you can see 36 line goes there. So you can imagine 36 vertical lines and its complement, and there are 16 output, that means 16 flip-flop sections are there that can be connected to this 16 IO blocks, or it can be fed back into this switch as input. Okay, so also you have IO blocks, those pins can act as input as well as output. So input pins can come as input to the switch. So all these that the output fed back or the inputs of 4 section come as the input, and output of the switch goes as a input to the AND gates input. Okay, so essentially if you take 4 kind of blocks like this, 4 macro cell section or 4 logic array block, then what we have as a switch size is see here 32 into 4, that is 128 inputs and 36 into 144 output. Okay, so it's a huge switch, and that is one disadvantage of the PLD. So you cannot stretch it to a large very large kind of device where a lot of macro blocks are there or macro cells are there. And we also have seen there are clocks which is going to the flip-flops. If it is not going there, you can use it as input. Similarly, output enable to enable the tri-state gate, dedicated output enable, or if it is not being used, it can be used as input. So we have seen that this is a crossbar, and crossbar is nothing but a 2x2 crossbar will have 2 2-to-1 multiplexer to choose any of the input for 2 outputs. So you can imagine n into n requires n n-to-1 multiplexer. So it is very huge in area and it cannot scale very much, and that is one issue which the field programmable gate array solves. Okay, and we had a look at, okay, this is that switch shown for clarity. We have seen that the feedback thing is coming as input, and the input itself is the IO pin input is coming as input to the AND gate, and the outputs are going to the logic block as input to the AND gate, okay. And this was a kind of architecture. We have in this MAX 7000 5 AND gates which can be connected to OR gate, XOR gate as a product term clock enable, or the asynchronous reset and so on, okay. And one of the AND gate is fed back into the array. So there are 16 sections, 16 AND gates as expander terms which can be used to cascade, okay. And if one section AND gate is not used, that can be used by the next section and so on, okay. So, and once again the problem remains here, these AND gates are very wide. There are a lot of inputs, there are 36 variables and its complement can be connected to the AND gate, which is very rarely needed in real life cases. So such a structure will make this 36 signal even make the switches, the programmable interconnect array or the crossbar very big, which doesn't make it scalable. So these two things are the one which is sorted out in the FPGAs, wherein you don't have such very wide product terms and you don't have a huge single crossbar, instead of having a central switch which is distributed across the device, okay. We will see the architecture so that it can scale well. So if you look at this particular CPLD, you can see the maximum number of the logic blocks in this device offers is 16, but if you stretch it more than that, then the huge area will be occupied by this crossbar and so on. So that is addressed in FPGA, and we have seen the flip flop as a cross recirculating mux built in. So if you can use one kind of clock enable, one level of clock enable for controlling the registers, and this we have looked at it, and we said some devices allows a direct connection from the IO pin directly to the flip flop, which can be used for synchronization. We have seen the metastability. Then when there are multiple clock domain, one would like to synchronize the input signal. So this can be used for fast synchronization. Otherwise it has to come through the crossbar, come in here, go through all the way for synchronizing, which will make the setup time very huge, okay. And many signals may not satisfy that setup time. So that is avoided by this particular fast input, which is shown in the picture like this, this MAX 7000S. And we have seen an example of a VHDL code, how it is synthesized and how it is really mapped into the MAX 7000 CPLD. And this shows the product time allocator of an XC9500. We can see that how a single AND gate is connected to OR or XOR or the clock or reset and so on. And this shows the product term steering part. If it is not used, it can be used by the top or bottom macro cell, or this can be combined with the previous one and can be used and so on, okay. So a lot of possibilities there, and this shows the IO configuration. You have a tri-state gate enable, which can be permanently enabled, disabled, or you can use various signal from the crossbar to choose to enable that, okay. So that add to the flexibility, and we have seen the timing model, which is very simple because between any logic blocks there is only one crossbar connection, and this all are specific to the macro cell, okay. So the timing analysis is simple, and the end-to-end timing is it's quite fast compared to probably an FPGA. But this device, since it is not very popularly used, it may not be fabricated in the latest device technology. To that extent it may be slow, like if you have a 22 nanometer technology, the latest CPLD, latest FPGA will be built on that, but the CPLD may not be built on that because the volume sale may not be that high. So that is why it is not built on that. So we have seen the features of that, basically and or very wide and or number of registers are small, timing is simple, architecture variation is small, the programming technology is flash and the capacity is around 10K. So what we are going to the FPGA, what FPGA addresses is this wide decoding is removed, a complex crossbar connection is distributed, and one more thing is that it basically gives you a lot of registers. Okay, so in a CPLD, register to logic ratio is very small. That means there are huge AND gates, number of AND gates are high, but if you compare to the logic, the amount of registers available in a CPLD is less. So you can't think of implementing some kind of memory structures, FIFOs and RAMs and all that in a CPLD, but in an FPGA. So we have seen some application where lot of FSM counters, random logic is needed. The CPLD can be used, but otherwise it is tough to use. It lacks of the memory affects these kind of application like communication, signal processing, cryptography and all is affected by those kind of lack of resources. But maybe simple cryptographic circuits can be implemented in CPLD. It depends how much what kind of algorithm you are implementing and how much is the key width and so on. Okay, so basically it depends on that, but then I am sure some small cryptographic circuits can be implemented in CPLD. So let us come back to the our topic of the today's lecture. It's field programmable gate array. So as I said, what it addresses is the 3 lacunae or 3 features in the CPLD. In the CPLD we have seen there is a crossbar which is very huge, which is a central resource which cannot be scaled. So in FPGA this particular point is attacked, and the interconnection architecture is distributed across the chip, so that chip can scale well. If you look at the number of logic cell in a FPGA, it will run into millions in the case of complex FPGA, which allows the designer to even emulate the ASICs in FPGA. Sometimes the complex SoCs require multiple FPGAs to emulate or to implement, but nevertheless this distributed interconnection architecture is the one which enables the FPGA to become complex in terms of the logic resources and memory resources. Okay, and the second thing it attacks is that we have seen that in CPLD there are the product terms which is very wide, which is not required in practice or in real life. So in FPGA you have the logic resources or the combination logic with smaller input, so that the area is not wasted. Okay, the resources are not wasted. The third thing the CPLD suffers from is the lack of registers, which is addressed very much in FPGA. In fact the FPGA balances the combinational logic with flip flop. So each logic block will have a kind of balance between the combination logic and flip flop. Okay, if you look back in CPLD, maybe there are 5 product terms, very wide product terms and 1 flip flop, but here you will have a much smaller logic in terms of the inputs. Okay, there it was kind of 36 input, but in an FPGA it may be 4 input or 5 input or 6 input, 7, 8 like that. No, I can say with all the combination and all the variation it start with number 4 and in a big logic block up to the 8 inputs. That's what is the FPGA targets, and there are a lot of flip flops. Okay, and many a times these logic combination logic is combined. Say you start with a 4 input combination circuit, then you combine multiple of them to make 5, 6, 7 and so on. Okay, so you get a lot of flip flops, because if you combine them, still you have the flip flops corresponding to that logic resources left out. So there are lot of flip flops available in FPGA. So the register to logic ratio is very high in FPGA, which allows you to implement a lot of communication or computer networks functions and signal processing blocks and so on. Okay, so let us go to the slides of this field programmable gate array. That's our almost we are coming to the end of the course. So let us see this. So we are going to the topics we are going to cover in a kind of from a very broader perspective is that we will look at the FPGA architecture of Xilinx. Mainly I will concentrate on the Xilinx architecture, and I will just show some Altera very briefly, Altera and Actel to contrast, and we will discuss the FPGA related design issues, FPGA related timing issues, the tool flow, how to configure FPGA, little bit about system on programmable chip or programmable SoC, whatever various device vendors call it. So you can call it PSoC, which is a programmable system on chip. That means the complete system like SoC is built on an FPGA fabric. How to debug the FPGA design, some case studies and so on. Okay, so that is the topic. The case study is definitely need not be very much linked to the FPGA. Yes, it is linked to the FPGA in the sense that we are going to implement that in FPGA, but this will kind of wind up put everything together we have learned till now, the VHDL, the digital design, advanced digital design, the FPGAs, CPLD, and all that will be tied together in the case study we are going to handle. So at the beginning of the course we have discussed the evolution of these devices. Okay, we have discussed the evolution of the PLDs in greater detail, but since we have discussed this at the beginning of the course, I will just briefly mention that ASIC is something which is built from the scratch. Okay, the designers might use some kind of standard libraries to implement this, the ASIC libraries, but more or less it's a huge kind of time it takes and huge cost, which is called non-recurring engineering cost. That means there's a one-time design cost, a lot of EDA tools are required, a lot of designers time is required, and one need to set up a foundry line to fabricate this. So all that is a one-time cost which has to be amortized once the ASIC yield goes up, because it's an electrochemical process, and at the beginning number of good devices out of 100 will be maybe only 80%. Then as the process is tuned you get 95, 98, 99. Then it makes sense to make an ASIC. So the trouble with ASIC is that since more or less it is implemented from scratch, designed from scratch, this cost, the NRE cost, will make it viable only for huge volumes, and it takes 1.5 years from starting to end for a reasonable complexity ASIC to come to the production. Okay. So this is one feature of the ASIC. So there is a middle ground where the cells used are fixed by the foundry, and they will give you libraries and you pick up the libraries and interconnect them. So only the interconnection is the unknown factor, because these the mask, everything for the standard architecture, standard blocks are available with the foundry. What designer once end of the design what goes is basically the interconnection of these standard blocks. Okay. So it is quicker, but the NRE cost is kind of medium, not as high as ASIC. So this will work for the medium volume. Maybe in a lesser time you can design, because you are working with standard block, and the performance will suffer because it may not be very much optimized at a complete system level. So there are design called mask programmable gate array. This means there are array of logic resources wherein it is interconnection is programmed at the foundry. So we can say, so this works for medium volume, and we can say the field programmable gate array is a field programmable version of the foundry version of this gate array. This mask programmable gate array or standard cell, interconnection is kind of fabricated in the foundry, but here the interconnection is configured in the field, okay, in a lab or in your workplace. So it is called field programmable gate array. Okay. Now when you say field, it is not the electric field, it means the field you are working, okay, the lab or something like that. Okay. If somebody is confused with that particular word. Okay. Definitely it uses devices where transistors where the field is kind of somehow involved in the programming, but that is not the name meant for. Basically, so that is the field programmable gate array. So it involves then the array of some logic resources, the interconnection with programmability which can be programmed in the field. Okay. So that is what is FPGA is about. Basically it is an array or a matrix of logic resources with programmable interconnection. Okay. So you have array of them, okay, not like in a CPLD you can't say array because it's the width is very less. You have 2 by 2 or like 2 in the width and 4 in the depth and so on, or 4 the column wise, the 2 row wise and so on. But here it is a huge array of logic resources with programmable interconnection. And if you look at the logic resources, we know that we have to ultimately do some computation using data path, which consists of combination circuit and flip flops, and that data path we are controlling by the finite state machine, which also require combination circuit for next state logic, output logic and all that, and the flip flops, the state flip flops. So we can say the logic resources in any reasonable design involves combination circuit and flip flop, be it data path or the state machine or controllers. So that is provided in the logic resources of FPGA. In particular, if you look at the combination circuit, the normal combination lookup table, the maximum used is the lookup table. We will see what is lookup table. We have discussed in a way in the case of CPLD, in the evolution of CPLD, but we will have a kind of a review on that. Some FPGAs use multiplexers as a combination logic, and you know that a 2-to-1 multiplexer, if the select line is connected to A, then you have A bar and A is available, or if you have a 4-to-1 multiplexer, you have 2 select line. To the select line you can connect AB, and depending on the inputs you get the output, the OR of the output. So and multiplexer is nothing but AND OR, so you form the minterm of the select lines variables, the minterms of that, and the programmable OR is achieved by connecting the various inputs as zeros or 1. Wherever there is 1, that minterm is a part of the output output variable, that is the multiplexer. Of course there are some FPGAs which use gates for implementing the combination logic. So that is about the combination logic. And if you look at the programmable interconnection, these are the technologies used: SRAMs, that is static RAM, and it's a bit of an unfortunate name, though at a kind of top level the name is correct, but it might kind of mislead you in terms of the technology used for interconnection. The flash transistor and something called anti-fuse, okay, or you can for the Americans is anti-fuse, okay. So here the anti-fuse is a kind of opposite of a fuse. You know that the fuse you normally pass a current to blow it, but the anti-fuse is something which doesn't have a connection. By applying a voltage you make a connection, okay. So that is called anti-fuse. And FPGAs has special resources like PLL, which is phase lock loop, DLL, delay lock loop, which is not used nowadays. Mainly all the FPGAs use PLL, phase lock loop, which has advantage over DLL. Maybe we will briefly look at it, though there is no particular reason, because the current FPGAs use PLL. Then the memories, RAMs, the FIFOs, the same RAM can be used as FIFO with additional logic. Memory controllers, sometime high end FPGAs need, since it has lot of computational possibilities or option of implementing complex computation. It needs a lot of memory, and the DRAMs are used. DDR3 can be interfaced, and in that case a DDR3 controller implemented in FPGA resource may be slow. So there are hard kind of controllers in the fabric. Network interfaces like the kind of physical interface or the data link of the Ethernet and so on, okay, or at least the blocks used in the prominent network interfaces. Sometimes the complex FPGAs has processors built in, hardcore processors built in, so that you can implement a complete SoC solution within an FPGA, okay. So that is a kind of nutshell introduction to the FPGA, its evolution, what it contains. It has evolved from ASIC, standard cell or FPGA and FPGA. It consists of array of logic resources with programmable interconnections. The logic resources basically is combination circuit and flip-flops, and the combination circuit used in FPGA varies from static RAM, the lookup table, then the multiplexers and gate. The programmable interconnection mainly uses SRAM technology, flash transistors and the anti-fuse technology, and there are special resources like PLL, memories, network interfaces, memory controllers and so on, okay. So that is the FPGA in a nutshell. So let us look at the slide. So if you look at the commercial FPGAs, these are the two major manufacturers who has a market, who shares the majority of the market, the Xilinx and Altera. Xilinx has a low cost devices called Spartan series. Currently they have Spartan 3 and Spartan 6. Though it is low cost, these are kind of still a lot can be implemented in a Spartan 6, complete. If you want a complete SoC can be built in medium complexity SoC can be built in Spartan 6. It is low cost, but that doesn't mean it's low complexity or low performance. It may lack some inbuilt processors and hardcore certain devices, but these are still powerful, and they have the complex FPGA. The previous generation was called Vertex 4, 5 and 6, and the current generation has Artix, Kindex and Vertex, kind of all share kind of similar architecture, but they have certain additional resources which is for which is suited for the IO requirement or signal processing and so on. Okay. The Xilinx also have a new devices called Zinc, which is nothing but a fabric like Vertex 7 plus dual core ARM processors are built in. Okay. That is not built into the fabric of FPGA, it is in the same silicon chip. So it's a hard ARM processor which can clock at very high speed. So a complete software hardware solution, high performance software hardware solution can be implemented in FPGA. When it comes to Altera, they have the Cyclone kind of low cost devices. Again, that doesn't mean it is kind of low performance or low complexity. They have Aria series and Stratic series, which is the complex version of these kind of devices. So, and they have soft core processors called Neos can be implemented in these devices, and the Xilinx has a soft core like Microblaze. Soft core means the design is available in terms of the Verilog or VHDL code. They have something called PicoBlaze, which is a microcontroller 8-bit, and the Microblaze is a soft core RISC 32-bit processor. Similarly, Altera has Neos 2 32-bit RISC soft core processor. Actel has different. All these are the static RAM based FPGAs, and when it comes to Actel, another manufacturer who has devices like Accelerator and RTAX and all that, which is anti-fuse based, and there are flash based Pro ASIC, and there is Smart Fusion with ARM Cortex M3 built in hardcore with this Actel. So Actel has a certain line of anti-fuse FPGAs which are quite useful in the space application, because it is a kind of a non-volatile technology. It's a one-time programmable. These devices, if it is SRAM technologies, are kind of, even if it's radiation hardened, programmed and sent into the space. Because of radiation, these memories can get the RAM programmable, like a configuration memory, can get corrupted, but not in the case of this radiation hardened anti-fuse, because it is permanently fused. But it has a great disadvantage, saying that it is only one time programmable. Once you program it, it cannot be erased and reused. So it's not very good for prototyping, like you can simulate, but then you want to test the system during the development. Not a good idea to use anti-fuse technologies. Maybe it has to be tried in static RAM kind of FPGA, then once it is matured can be transferred to the anti-fuse kind of technology. So essentially in a nutshell, this may not be a very accurate picture, but at least the previous generation of the FPGAs had this kind of architecture. The current ones, I cannot say that it's exactly this, but then it's a good starting point, and it is it's quite correct, but there are additional details in a current FPGA. So let us look at the structure of an FPGA. So basically you have IO pins around. Of course there are VCC, the ground pins and all that, plenty of them. For the inner core and the IO pin. So normally the core works at a low voltage and the IO pin works at much higher voltage. So this may be under 1 voltage, but then when it comes to the IO pin it may be 2.5 or 3.3 volt devices depending on the technology. Otherwise there are a lot of IO pins around, and you can see that there are logic blocks, array of them. Okay, here it is only shown 4 by 4, but in real life it can be my say huge number, 32 by 32 or 128 by 128 and so on, even higher sometime. And these are kind of wires all around. So you can see that this may be multiple number of wires which is connected in a switch here. Again the wires, all the wires are connected in a switch here, and this the bottom and the left are the input to the logic block. And so then that means there is a switch here, and this the top and the right hand side is the output. So in principle how the design is done in an FPGA is that the synthesized logic is placed across multiple blocks depending on some kind of constraints, and say an IO pin can be connected to the input of a logic block, and that output can come here. Maybe it can be taken to the input of this logic block, as well as come all the way and to this logic block, and this output can be maybe taken to the input of this logic block and so on. So basically this structure allows you a lot of possibility of connection, and you can see that it's not a single switch like CPLD. In the CPLD there were logic blocks and there is huge switch, but here these are kind of similar blocks, very small logic and flip flops, and a lot of them are there, and it is interconnected through a lot of wires and lot of switches which is distributed, so that it can be scaled big. You can have a much bigger device than CPLD. And so these maybe there are when you talk about switch here, need not that all the wires from this switch run to this switch. There could be wires running from the first switch to the third switch, first switch to the fourth switch and all that. So there could be wires which is a kind of single length of the single block, or we can say single length wires, or double length wires, or quad length, or the wires running from one end of the device to the next end of the device. Otherwise these kind of wires, different length wires are required, because otherwise suppose there is a logic block here, the output of which need to go to the input of the logic block at the end, and if you connect by single length wires it will incur lot of switches are required for interconnecting them, which wastes the area of the switches, and it will incur lot of delays. For each switch there will be delay, and so end to end delay will be very large, and the maximum frequency, because we have seen in a data path the frequency achieved is TCQ plus TCOM plus T setup, and here the combination delay will include the combination delay includes all the wired delays, the interconnection delays, and in an FPGA if there are a lot of switches used, these interconnection delays will be more than the logic delay. So that is one issue with the FPGA. There could be interconnection delays which is much larger than, sometime more than the logic block. It depends where the logic is placed within the chip. Maybe if you have some logic here and the output is taken all the way to the right hand side of the FPGA, which is very huge, through lot of switches, then it incurs a lot of delay. So that should be kept in mind. The interconnect delay is one kind of disadvantage of this FPGA, but that is at the cost of flexibility and cost of scalability of the device. This distributed interconnection is what allows it to grow in sizes, but that add to the end to end delay when the circuits are placed and routed within FPGA. Okay. So this shows a little more detailed diagram. So this shows the CLB you can see here, and these are the switch blocks all around it at the corners, and these are wires. You can see that this shows that the 4 wires are kind of connecting this switch to here, and you can see there are maybe 7 wires connecting horizontally, single length wires, and these are the input to the logic block. And CLB means it is called configurable logic block. Okay, that is one thing once again you should remember, that not that the wires are programmable or configurable, what logic within the logic block is also configurable. So there is not only programmability in terms of interconnection, there is programmability within the logic block, okay, to make it very flexible. So when you say configure FPGA, it means configuring all these connection as well as configuring the logic block, okay, that should be kept in mind. So it's a configurable logic block, and you can see that means that there are switches between this input wire and the output wire and so on. Okay. Similarly this shows an output of a logic block is coming to a switch here. It essentially means you have either you can connect this output to this input, this one or this one, or maybe this side, it doesn't matter, you can connect it either way, or sometimes it's a single line to which it is connected, or there is a disconnect depending on the number of outputs and so on. Okay. So it depends on the vendor, and vendor does analyze a lot of applications which is mapped into this kind of fabric, and from the statistics they have to make a judgment on how many wires to place and so on. Okay. So it's not that the number of wires and type of wires are fixed from device to device, depending on the complexity there could be more wires or less wires and so on. Okay. So that should come from statistics. Normally this cannot be blindly put, maybe they started analyzing the applications and put some wires in earlier generation. Now they keep statistics of the current applications, and when they evolve to the next family of devices they kind of scale it appropriately, these number of wires, the type of wires and so on. Okay. And if you look at the interconnection itself, this is how it is interconnected. The switches which is shown here, so you have vertical wires and horizontal wires. So what is done is that between a vertical wire and a horizontal wire you have a transistor. When the gate is made on, it is interconnected. Okay. And you can have a unidirectional connection or a bidirectional connection depending on your need. Maybe if the output is coming from this side and going to the input on the other side, you need only a unidirectional, but if there is some kind of data flow, signal flow in both directions, then you need a bidirectional switch. And now if you look in principle, if you have a 3x3, this can be connected not only to this, it can be connected to this as well as this, and maybe yes, say each of this line can be connected to 3, but sometime providing all possible connections can make this very huge. So many a times it's not that a single wire is connected to every other wire and so on. Okay. Particularly there may not be any connection between the vertical and vertical wire, there is no need, because we have seen the output is coming to all vertical lines. So normally the vertical lines are connected to the horizontal wires, but here when it comes to a switch box, this part need to be connected to this vertical line to cut through. Okay. So that connection is required, that is you can see that it is shown here. So there is a vertical connection here, okay, and a horizontal connection here. So there are various switch architectures. You can see there is a disjoint connection, and wherein one each wire, the vertical wire is connected to two horizontal wire and one other vertical wire. A slightly different method of connecting, again slightly different method of connecting. So you have the choice, you need not be that this wire need to be connected to this horizontal wire, maybe it can be connected to the some other wire. So in this case you can see that the first wire is connected to the topmost horizontal wire, but here the first wire is vertical wire is connected to the bottommost horizontal wire. So there are different architectures. So depending on that is a little bit of a back end detail of the device. So as a designer we need not bother too much about it, but as a device if you are in the FPGA design, you are designing the FPGA device, then one need to bother about it. So we are basically looking FPGA as a device to program our device design. So we need not, we need to understand, but we need not go into the details of various interconnections and so on. So let us go to the next level. So this is a very old slide from the Xilinx data sheet. So that but illustrates one thing. In FPGA you would have seen, we have discussed there are a lot of combination circuit, flip-flop. So there will be lookup tables, flip-flops, interconnection, wires, switches and all. But then you know that all these need to be configured, like switches need to be programmed on or off, the logic block need to be configured and so on. So there are a lot of overhead configuration circuitry, that means is configuration pattern need to be stored somewhere. At the power on these switches need to be programmed and so on. So you should know that the FPGA is not just what the designer sees. The designer mainly see only the logic resources, flip-flops and wires, but there is an underlying configuration overhead logic and the circuit. Okay. So that makes the FPGA quite big, these wires and the switches and the configuration overhead circuitry will make the FPGA much bigger, it will be spread out. So you can expect at a raw speed the speed like ASIC for FPGA, but there are in FPGA you can exploit that it is a programmable fabric, and it is in the control of designer to put however many computational unit within FPGA. Maybe we will do very wide computation, like we get 32-bit data, we might choose to convert it into 64-bit data or 232-bit data and do it parallelly, do it at a much higher data width and so on to achieve performance. So though FPGA lacks in raw clocking speed, maybe an ASIC will clock at say 1 gig or 2 gig, maybe FPGA will clock only at say 200 megahertz or 400 megahertz at the most when reasonable complexity design is put into it. But by design techniques, by doing wide data computation, multiple cores and so on, you can replicate the number of computational units, you can do a lot of parallel computation and achieve the performance maybe bigger than much bigger than the ASIC. Okay. So there is another disadvantage of FPGA, the power dissipation will be quite high compared to the ASIC because of the huge area, huge interconnection, and naturally the power dissipation will be much higher, and you may not, because these are pre-built the resources, very custom low power design cannot be done in FPGA because the application is not very evident. So very aggressive low power design cannot be done in an FPGA as in ASIC. So on 3 counts, say the raw speed, the power dissipation, the FPGA suffers, but then definitely you can achieve high performance with a lot of flexibility of programming, reprogramming, configuring, the FPGA will be able to achieve. So let us move on to the slide. So essentially if you look at the FPGA, you have IO blocks, and this we didn't discuss. The IO blocks always contain, you see there are the tri-state gate based output, so which can be used as input. So these are IO pins, and there will be always a synchronizing flip flop. So we have seen the need for synchronization because this input is coming asynchronous to the clock we use, which usually will be the case because we will supply the clock to the FPGA. Everything internally will be clocked by that clock. Maybe the signal which is coming from another chip may be clocked by another the clock. So this need to be synchronized. So there are synchronizing flip flop, single stage synchronizing flip flop within IO, and it support multiple IO standards. So it may be working with 2.5 or 3.3 like low voltage CMOS, or it supports some kind of the voltage pattern which is ideal to the PCI Express or PCI and so on. So all that is supported in an IO pin. So that is IO blocks. Then you have array of configurable logic blocks. We have said the main thing to note is that it's not fixed, it is configurable. A lot of configuration is possible within logic block. Then there are horizontal and vertical wires with programmable switches in between. We have seen that there are horizontal and vertical wires with programmable switch. Then these wires could be single length, double length, quad, hex or long lines, and there are resources available to the user, basically the logic block, the flip flop. Then there are resources for configuring the programmable switch in the interconnect sectors and logic block. Okay, so there are a lot of programmable circuitry which program these logic blocks and program the interconnection of the wires. Okay, so that is in a nutshell it is an FPGA, a simple FPGA. So in addition high level FPGAs will have, as I said, DSP blocks, the hardcore memory controllers, the network interfaces and so on. So we have covered the essentials of the field programmable gate array. So let us look at this particular programmable connections which is available in static RAM based FPGA. As I said, this SRAM is a bit of a unfortunate name. The interconnection technology used is a pass transistor, and we will see why it is called SRAM. Some FPGAs use flash transistor. We have seen that in the case of CPLD, and some use a technology called anti-fuse which is opposite of that of a fuse. So let us look at the static RAM. This shows a FPGA architecture with say 4 configurable logic blocks, wires, horizontal wires, vertical wires, and switch interconnecting the vertical wires, and this shows that output of a logic cell is connected to the vertical wire. So the connection is an NMOS transistor to connect that, pass A0, and so basically if this N transistor is on, the output is connected to this input, and similarly this vertical wire has a connection to the horizontal wire using an N transistor. So if the gate is made high, it connects. Okay. Now the problem with this kind of SRAM FPGA is that it cannot remember, it is not the state of the gate of NMOS transistor is not stored permanently. So at every power on this need to be programmed. Okay. So if you look at what can hold a bit, a single bit is a flip flop. Okay. So at the gate of each pass transistor is a flip flop, and now when we say we program, we are programming the flip flop as 1 or 0. Okay. So that can be, so there is a flip flop here, and if you see there is a 2-to-1 mux. You see here there are say a lot of lines, lot of horizontal lines, and now you can have a kind of crossbar connection. We said that n by n crossbar uses a n to 1 multiplexer. So basically the multiplexer is the one which is, so this is a kind of 1-to-1 multiplexer, but here you can think of say 4-to-1 multiplexer, which allows you to connect any of the 4 horizontal wires to be connected to the input of a logic cell. So here if there are 4 inputs, then you have 2 select lines, so there are 2 flip flops connected to the select line. So if you have the ability to program 0001, 1011 and so on. So now so you can imagine wherever there is a switch there is a flip flop. Now you cannot program these flip flops individually, so what is done is that these flip flops are collected together as a static RAM or as a memory which is 8-bit or 16-bit wide. In the previous generation it was 8-bit wide memory, in the current generation it is 16-bit wide. So to program means you write to this configuration memory which is SRAM, but the real interconnection technology is a pass transistor in an SRAM type of device. So I think we are coming to the end of the lecture. So before I think we, instead of going further, because then we have quite a bit in the programmable interconnection, so let us wind it up here. So what we have seen is basically general architecture of the FPGA, a lot of IO blocks, configurable logic box, and which is distributed across the chip area, the programmable wires with switches in between, which is again distributed, not a single switch, it is like array of switch with the regular wires laid. So the logic blocks can be interconnected through that, and when you look at the logic block itself, it is a combination circuit and flip flop. Combination circuits are lookup table multiplexers of gates, flip flops. Then the interconnection technology is static RAM, anti-fuse, or the flash kind of devices, and so that is what we have essentially seen about the FPGA. We have seen the commercial Xilinx, Altera and Actel devices. We have seen some of the families of devices. So the last part was the programmable interconnection. We have seen the SRAM kind of technology. So in the next lecture we will continue with this programmable interconnect technology and go to the architecture of the FPGA to understand in deep. So I wish you all the best and thank you.